All right, last time we were talking about the concept of determinism with respect to push-down automata, and we found that it was actually a separate class of languages. There was no one-to-one mapping between a language that you could construct an NPDA for and a language you could construct a DPDA for. So we learned that we need to think about exactly how to make that transition if it is possible. So we looked at lambda transitions because in a DPDA, you can actually have lambda transitions. The issue is that you can't have two different lambda transitions out of the same state that consume, well, one that consumes no input character and one that consumes an input character, because that creates a very interesting choice. And we found that whenever we have determinism, we need to know what move we are going to make given our state. And that would allow multiple different moves, which means we would have to go explore both of those paths deterministically, which is not allowed in a deterministic automaton. So it's important that we do still allow those lambda transitions though, because we know the stack is part of this state. So we need to be able to modify the stack as we make those lambda transitions. It could be that there is something that we want to do. We want to make two different moves with the stack, potentially, and so we can move the stack, manipulate the stack without moving through our input. So the way that I introduced the concept of determinism here was that at all times, at most one possible move exists given the state that we are in. And remember that the state that we are in is now not just the state in the automaton, but it's also the top of stack character. So given a pair of state top of stack character, we should only be able to make a single move. And then we said we could freely convert between DFAs and NFAs within regular languages, but we have no such conversion in the push-down automata world. So only some non-deterministic push-down automata have equivalent deterministic push-down automata. So I wanted to have an example of this. So let's have two languages. The first is A to the N, B to the N. We saw that this was context-free, right? We proved this. The second one is A to the N, B to the 2N. So let's start with the question of why was the first language context-free? Kind of however you could put this into a single sentence. I find a pen that has some juice. Little bit more. We're feeling orange today. So yeah, this first language is context-free because I like to think about mapping this to stacks and memory. If we store all of the A's as we go through the first half, all of the A's, once we start seeing B's, we can start mapping every B that we are seeing to an A that we historically saw, which maps perfectly to this concept of a stack. You push all of the A's, and then you pop all of the A's as you map them to an associated B. Great. So when we see an A, push something that shows that we did that, transition on seeing the first B. When we see a B, pop one of those characters off the stack. Great. How about L2? Taking that kind of logic how could we think about L2 being context-free? Hi, hi. We have one person on Zoom, so I've been lecturing to an empty classroom. So to give you the quick recap, we talked about determinism at the end of last class. And we talked about how there were different classes of languages for non-deterministic pushdown automata and for deterministic pushdown automata. So we're moving on to an example here and thinking about the intuition behind these couple of languages. The first language is A to the n, B to the n. The second language is A to the n, B to the 2n. So the intuition for why the first language was context-free is using a stack. We can push something onto the stack for every A that we see. And then once we see our first B, we transition and start popping those characters off the stack, matching a B that we're seeing now to an A that we saw some time ago. If the stack ends up empty, then there were the same number of A's and B's, and all the A's came before the B's. So the question I have now is, given this second language, why would this be context-free, given that idea from the first language? So now we have twice as many B's following the A's. How would we map that to the concept of a stack? So the intuition for this second language is that when we see an A, what we want to do is, instead of pushing a single character, we want to push two characters. If we pushed AA, capital A, when we saw an A, then when we see a B, we could pop a single character. So when you see an A, you push two. When you see a B, you pop one. And now if the stack ends up empty, you end up mapping each A to two Bs. So thinking about how to do this in terms of a stack makes it really significantly easier, at least for these baseline examples, to see why these languages are context-free. So CNA push two of them, transition on seeing the first B. When we see a B, pop an A. Exactly the same idea, except now you're pushing two A's because you expect to see two B's for each A. Because you know this when you start, you can manipulate the stack in such a way that you expect to see that. Now we're going to, with this knowledge, we know both of these languages are context-free. We can use stacks to recognize both of these languages. We're going to define a new language, a union of these two languages. The question I have for you is the language context-free? If so, what's the intuition that tells you this language is context-free? If it's not context-free, come up with an argument for why you don't think it is context-free. For the couple people who just walked in, you would never guess that 4 minutes ago I was lecturing to an empty classroom.
I don't think it is right. You got today in the middle.
It's an interesting idea. We have one vote for this language is not context free. Let's put this to an intuition vote. I'm also going to see the effects that this one vote had on everybody else's vote. Who thinks that this is not context free? Two votes. Who thinks this is context free? One vote. We're at least split. I love this. Whenever we have votes on both sides, I love this. Interesting. We have two votes for context free. So it is context free. Why? People assume just because there's a question here after the examples of something that's context free, that it wouldn't be context free, which is usually true. That is usually how most people give those examples. But this is a context free language. What's the intuition for why that is? Either one of the people who thought it was context free? What led you to think that?
Context free makes the other stuff context free.
Potentially. Why would that always be the case? Let's come up with the intuition for why unioning two context-free languages might always be context-free. Then we could either come up with at least some kind of intuitive argument. It's not going to be a rigorous math proof, but at least the intuition behind it. So we know that a context-free grammar exists for anything that is context-free, right? So even though we have some logic here, we know that we could generate a couple of grammars. So let's say that we have G1 that represents this grammar for L1. And we have G2. I'm going to basically say that G1 starts with S1 arrow something, and G2 starts with S2 arrow something. Right, doesn't matter what the rest of the grammars are. We know they exist because these languages are context-free. And we could write them pretty trivially. These are not hard grammars. I just don't want to go into it. We could write one more rule at the top of this that says S arrow S1 or S2. And now we encapsulate all of this into a new grammar. Why does this work? Why is this something that we can do? What is it taking advantage of? It's taking advantage of non-determinism. If that makes sense. For this to be deterministic, we have to be able to make this decision about which grammar we're going to go into when we see the first character, because there's no character here. So we have to make our decisions, and there's no teleporting between these two grammars. We can't be in the middle of grammar 1 and switch to grammar 2, or be in the middle of grammar 2 and switch to grammar 1. We have to know when we start what form this string is going to adhere to. So when we see our first A, which language are we in? Are we in L1 or L2? Who knows? So deterministically, we would need to know here. Non-deterministically, we're just going to say, all right, we're going to go explore both at the same time. If we happen to get success back from S1 or S2, then we accept, but we're exploring them both at the same time. Deterministically, now we have to explore one and then the other. So that's kind of the intuition behind why there is no such deterministic solution to this union language. There would be deterministic solutions to either one of these languages. Because there's only one way to do it, but now suddenly we have to make a choice between which grammar we go explore. And there's ambiguity when we see those first few characters, and there's no way to know. Even if you saw some A's and then your first B, would you know at that point? Like, let's say we saw the string A, B, and we know there's more to come yet, but we've parsed this far. What do we know? Nothing yet, right? We still, even with this read ahead, could be in grammar 1 or grammar 2. We have to answer the question, which grammar is it in, to know which grammar to even start looking at. Which is kind of an interesting conclusion, that you have to have the answer to even start. All right, slide's gonna walk us through this, but I like drawing it out first. So the grammar decides immediately which form the associated derivation will be. We need to decide right from the beginning whether we are generating a grammar for L1 or L2. And we can't do that without parsing the entire string. So this is logic that is possible in an NPDA. We just allow two different out edges that when we see that first A that says one of these is going to go down the path of exploring language 1 and accepting language 1. One of these is going to have to go down the path that explores language 2 and accepts language 2. Since it's non-deterministic, we just do them both at the same time. Determinism, on the other hand, would have to be able to choose from the beginning, and there's no way to do that. And again, I don't want to confuse this intuition with a proof. However, I would much rather deliver this to you and not the proof, because now you can go read the textbook proof, and I think the textbook proof will map directly to this logic and this idea. Rather than if I gave you the textbook proof without any of the background for why the proof works, you'd be kind of lost. I would be kind of lost. So if you're ever asked for a mathematical proof, this is not enough. So let's talk about how do we write grammars for deterministic context-free languages. So we want to be able to study deterministic context-free languages. Why? They can be efficiently parsed. This is something that we're going to come back to when we start studying compilers the last couple weeks of the course. Because even a cubic algorithm isn't really going to be good enough for parsing certain aspects of programming languages. We're going to want a linear time algorithm. And it turns out that a linear time algorithm does exist for deterministic context-free languages. And a cubic one exists for non-deterministic context-free languages. So we'll come back and really look at these in a lot more detail later, but the idea is you only have one possible move given the pairing of the state that you're in the DPDA and the top of stack character. Given those two things, there's only one possible move that you can make. We know that we can terminate in a number of moves that is proportional to the size of the input string. No cubic times CYK algorithm needed here. We can use a linear time approach. And in fact, we'll talk about exactly how that process is done. Those are LL and LR parsing methods. So we will certainly come back to this, and it actually is your second project idea. If we get there soon enough, then you can decide to do that instead of CYK. Although I still recommend getting the CYK started and done, but it'll be an option for you. So we did introduce the concept of a simple grammar a while ago, but here is where they're going to be used, using a simple grammar and using LL and LR parsing to parse them. So the basic idea is we get a simple grammar. There's only one choice of which production to apply given the current input symbol. So we're looking at the string, we're looking at the next character, and we say, oh, the next character is an A. Even if it's some number of derivations down the grammar, we can still somehow go see there's only one way, given the top of stack character, to consume that input character. There's only one sequence of productions to go down. So we just need to go find it. Did I not animate this next slide? No, I guess I stopped early. That's awkward. So I guess we can talk about this. So basic introduction to this concept that we'll come back and explore the exact algorithm for later. We need to be able to parse what we're going to call less restrictive grammar types, LL grammars. We want to look at the scanned symbol. We have some number of yet to be scanned characters that are to come. So we want to be able to predict which production is used to generate the query string. So let's use this example. We have a two production grammar, S arrow, A capital SB or AB. This is LL2 because to be able to decide which production to apply, we need to be able to look at the next two characters in the input string. Does that make sense? So if we are at this point where in our grammar, we are at the top of stack symbol is an S. So here's the stack. We don't know what's beneath it. We just know that an S is on the top. We look at the input string and we see A. In an LL2 grammar, we need two look-ahead characters to determine which production to apply. What production do we need to apply in order to generate AA? Any thoughts or ideas? Yeah, it has to be the ASB, right? Like there's no way we can produce this if we decided that we're going to take this production here, S arrow AB, no way we can generate AA. But if we do A capital SB, this capital S could become something that starts with an A. So the idea is that we're going to replace this S. The next move is this is going to be a B, an S, and an A. And now when we resolve this S down here, this A gets mapped to that A. And we're left with SB on the stack. And this S can now produce that A in two different ways. So the only way to generate those two was to take this S and make that ASB. On the other hand, let's say, rather than doing any of this work, we're back in the world where we're looking for AB. Are there one or two options for mapping this sequence to come in the string to what we should do to this S? Yeah, it's just AB. If we do A capital SB, that capital S has to start with an A. So the only way to do this is to replace this S with AB. We can now map this A to that A, this B to that B. We pop those off, mapping them to this. And now whatever is below this S is what we're going to start parsing next to whatever's left in the string after that. So a grammar can be LL of something, some constant, if that constant is the number of look-ahead characters that we need to be able to guarantee that there is only one path through the grammar that can produce that particular set of characters. And you can see how this starts to be linear now. You look for this and you try to generate, can this produce that? Can this produce that? If you have a way of stating those rules in advance, then you know immediately based on a lookup what to apply. So that is a very short preview of the last couple of weeks of the course, because this is very important for efficient parsing in a compiler. I don't know if I want to go through this in too much detail because I know we cover it later, but you can ask questions like, is this grammar an LL grammar? So assuming we just scan the first symbol, the first symbol is an A. Do we choose SS or ASB or AB? We don't know. We scan the first two symbols and we see AA. Do we choose SS or ASB? We don't know. If the full string is AABB, there's one path through this that requires a capital SB. If the full string is AABBAB, then we need to select SS. So the grammar is not LL of 2. And it turns out that no matter how far ahead we look, there are always multiple strings that can cause us to want to choose different production rules. So this is not LL of any constant. If it's not an LL grammar, we may be able to convert it into a grammar that is LL of some constant. So different equivalent grammars have different LLK values. So is that grammar equivalent to the top grammar? It turns out no matter what path we go, A has to start the string in the top grammar, right? No matter what we do, there has to be an A there eventually. So we know that we can factor that out into lowercase a. Since now S can map to nothing, this second capital S, the first capital S in the right-hand side, can now be anything from there. So yes, this actually is equivalent. Now, we can determine with a single look-ahead character whether we're in this world or in this world. We can determine if it's an A, go here. If we're at the end of the string, go here. So suddenly we converted it into an LL of 1 grammar. Of course, we can generate lambda. That's not great. This could not generate lambda, except in the empty string. So now we just do this. If you factor this rule out and make equivalences here and kind of move the lambda to here, now we're forcing this rule to be applied at least once. Which tells us we no longer accept the empty string, but afterwards we can now terminate from there. So again, we're going to be returning to this when we discuss compiler parsing, but many compilers have been written using LL parsers. So it is a very common method. So it is very important for you to know if you want to be able to understand a compiler or to write your own. Questions? We're going to pop into our favorite topic. We can guess that just like we were able to prove that a language was not regular with a pumping lemma, if we wanted to prove that a language is not context-free, we would also need to do something fairly similar. It turns out to not be identical. In fact, is fairly significantly harder. However, if you understand the pumping lemma for regular languages, it is much easier to understand the pumping lemma for context-free languages. They map onto each other very nicely. So learning the first pumping lemma, really challenging. Learning the second pumping lemma, even though it's harder, based on your knowledge of the first one, is really important. So what I want to start with is just kind of a show of thumbs. How do you feel about the regular language pumping lemma? Anyone whose thumb is not, yeah, I expect to see you in office hours sometime before the exam about the regular language pumping lemmas on Friday. There are lots of examples that I can go over, and in fact, I may even take tomorrow's class as well as Thursday's class. Maybe I move the review forward a day because I think that there's a bit that we could do with that. I'll think about that, but maybe you'll want to attend tomorrow's class really a lot too. We'll find out. So I guess we'll start. We'll see how the next 18 minutes go. What was the pumping lemma for regular languages? Looking over some of the homeworks, I did see a few of the common mistakes that I expected to see. So we knew that, of course, all regular languages exhibit some kind of repetitive pattern. I should say all infinite regular languages. The idea was we wanted to, assuming that there was a DFA that represented this language, you could get to some looping construct, get from the start state to a looping construct, iterate that looping construct some number of times, and then traverse from the looping construct to a final state. And we called this concept XYZ. X mapped to getting to the loop, Y was the states that iterated the loop, and Z was getting from the loop to a final state. If there exists a string in the language that does not adhere to that particular pattern, the language is not regular. And again, I said that you could visualize this with the number of states in the associated DFA. For context-free languages, rather than looking at the number of states in a DFA, we are instead going to visualize this by looking at context-free grammars, because this turns out to be way easier than trying to visualize this through NPDAs, because visualizing NPDAs in the first place can be pretty challenging. So it makes sense to kind of take a grammar-based approach for finding the intuition behind this pumping lemma. So we are going to look at context-free grammars. So some differences between these two pumping lemmas. How did we produce an infinite number of strings given the, or in the process of the regular language pumping lemma? We turned this concept of X, Y, Z, which was getting to some looping construct, iterating a looping construct, and getting to a final state. So here is kind of the starting state, and here is some final state. So here is kind of how I visualize X, Y, Z. You can create an infinite number of strings using this idea by just saying, how many times do we go through this looping construct? Since we start and end at the same place, we can do this an arbitrary number of times. We could completely remove this Y and just do XZ. That gets us directly from the initial state to the final state. I guess I should probably draw this a little bit better. We're gonna do this. And now the Y is over here. That's better visualized, because now we can have XZ without, we can take out the Y without affecting getting to that final state. So this would be X y sub 0z, or just xz. You can have x, y, z, which gets here, iterates the loop once, gets to a z. Or does the z gets to a final state. X, y sub 2z is we're gonna iterate this, the loop, and then going to the final state. So because I can be the positive integers plus 0, there are an infinite number of possible strings that we can generate from this breakdown. If in any one of these, we can produce a string that's not in the language, then this DFA that we've constructed in this form recognizes a string that's not in the language. In any infinite regular language, there is such a breakdown. So that's the basis of the proof. Now, instead of looking at the DFA where we start here and end here, we're going to instead look at grammars, but it's going to be very similar kinds of logic. We need to be able to produce an infinite number of possible strings in a language, just like we could in an infinite regular language. In a grammar, this means that we need some loop within the grammar. We need a way to be able to take some non-terminal via some constant number of productions. We're going to be able to produce that non-terminal again. Think of it like recursion. It's very short if you have a production that looks like this. We've seen this a few times. Within a single production, we've been able to produce an S from an S. This means there are an infinite number of strings that this language can generate, right? We can generate AB, as long as we can terminate this somehow. We can terminate AA, we can create AABB, AAABBB. With this single production, because we have this insertion in the middle here, we can very easily iterate this an arbitrary number of times. So it maps very similarly to that concept of a loop in a finite automaton. So we need some way of showing this recursion in a grammar. So that's the first thing to look for and note, is that we're going to be looking for recursively defined grammars. I'm going to start using some letters kind of like X, Y, Z, because this is going to become the middle of our proof. So if we have A arrow, V capital A Y, and A arrow some star X here, we're going to be able to chain these together to be able to produce this. Right, we have an arbitrary number of V's on the left side, an arbitrary number of Y's on the right side, and a single X that terminates the grammar in the very middle. Does that make sense? The number of times that we go through this loop produces this many copies, and then when we decide we are done, we apply this rule that gets us the X in the middle. Two important conclusions from this that are different from the conclusions of the regular pumping lemma. First of all, what are these differences? If you were to look at the concept of X, Y sub I, Z, how does that differ from this logic here? Different. How many parts of the string get pumped? We have 2 instead of 1. We're pumping the V's and the Y's, keeping the X constant. Here, we pumped the Y and kept the X and the Z constant. So 2 possible places that we are pumping. The other important note is that this pump can actually occur anywhere in the string. When we were able to look at this world right here, we knew that this pump had to occur within the first M characters because M was the number of the number of states in the DFA representation of that language. That was a very important rule. That exact rule does not exist here. So we're going to have to do something a little bit more complicated that's going to require usually a lot more thinking to try to generate and construct this proof. So given this background of why this works and how it's a couple of ways that it's different from this, let's actually introduce the concept of the pumping lemma for context-free languages. We're going to say let L be some infinite context-free language. This means that it can generate an infinite number of strings. This means that there is, again, a positive integer M, such that any string in the language with length greater than or equal to M can be decomposed into, now instead of 3 parts, we're going to have 5 parts. U, V, X, Y, Z. There's the following constraints. We know that Vxy, this center part, must be less than or equal to M. The length of the 2 components that actually create additional strings from this recursion has to be greater than or equal to 1. So Vy, when you're looking at these components, this is what got pumped in the last example. We said that X was kind of that middle segment, and this is what the left and right side of that got pumped to be able to create the recursion that allowed us to infinitely recurse and create an infinite number of strings. So we know that this length has to be less than or equal to M. And now M, instead of being the number of states in the DFA, is going to be the number of productions in the grammar. Why does that make sense?
The protections have to be able to,
Yeah, we have to be able to recurse and generate one of those. So let's say, we have something like A arrow, doesn't matter what the terminals are. B doesn't matter what the rest of the non-terminals are. We now need to define B. If we define it in terms of A, there's the loop. The loop is 2, we have 2 productions. In the worst case, we need some other production. Some other sequence of productions. This could be some C's, some D's, doesn't matter, but every new non-terminal that we get to has to be a new non-terminal that we haven't seen before. Otherwise, there's your recursion. So in the worst case, there's a single non-terminal here. And in the worst case, there is some new non-terminal. Every time we write these, we need a new non-terminal. Eventually, if this grammar is capable of producing an infinite number of strings, there must be that recursion. Maybe D is written in terms of either A or B or C. But now we have within some number of productions, 1, 2, 3, 4, the ability to define A in terms of A. That is the most productions that could possibly be. Within the number of productions of the grammar, we have to be able to do that. So this would tell us that the length of what's being pumped here, the length of this entire string, that recursion has to be defined within this many steps. So this is in general what is happening. we're going to get from the start state of the grammar to this first instance of the non-terminal that is going to be recursed. As we do this, what string gets produced? Well, there's going to be a front end to the string, and there's going to be a back end to the string that is getting from the start non-terminal to the beginning of this recursion. So it's, again, a very similar idea to a DFA going from the start state to the looping construct, but now we're starting at the start non-terminal and getting to the recursion. Then we need to define what happens between that, the start of that recursion and the next iteration of that recursion. That's what's going to generate the V and the Y. When we do that, now we need some way to terminate the grammar, and that's what produces the X. So just like before, we had an intuitive understanding of what the X and Y and Z were, going from the start state to the loop, iterating the loop, and going from the loop to the end. Let's actually write down exactly what these represent. So U is your beginning of string generated from the start non-terminal to the tell us the recursed non-terminal. And in this case, Z is just going to be same thing as U, but the end, not beginning. Very official definitions. Wow, that is curvy. Looks so much worse. So this is the same as this. It's the end of the string generated from the start non-terminal to the recurse non-terminal. Then we have V and Y. So this is the I'm going to go from beginning to front because this can be done at the front of this rather than the beginning of the string that's done. Front of string. My terminology is very official here. It's the same thing as V, but it's the back of the string generator iterating the recursion. And then X is the string that's generated from the recursed non-terminal to termination, whatever that means. We need to be able to get from A to having no non-terminals. Whatever that path or process looks like, that's what's going to generate the X. So here we have 5 definitions for these 5 components, U, V, X, Y, Z, and the only parts that get pumped are the V and the Y. because this is the only part of this process that is repeatable. This is what defines the recursion. We can do this recursion 0 times, we can do this recursion 1 time, we can do this recursion 10,861,224,106 times. Doesn't matter. Arbitrary number of times, however many times we do it, that's how many V's and Y's appear in this string, whenever those substrings happen to be. Make sense? Drilling. It's important to know. It's one of the more challenging parts of this course. And I find that it's much easier to be able to construct these proofs if you have an understanding of what these components actually are. Get to the recursion, iterate the recursion, get from the recursion to being able to terminate the grammar. So again, it's 3 components, but we now have to think about the beginning and end of strings because now we can insert in the middle. We could not do that in regular languages. We either had to insert at the beginning or insert at the end. Thinking about it in terms of grammar, this was the left linear and right linear. We had to start at one end or the other end and generate the string from the beginning or from the end. And now we can insert in the middle. When we insert in the middle, we have to consider the beginning and end every time we do this. All right, we are over time for now. So I'll come back tomorrow. If it would make more sense diving into this and starting to do the proofs to go back and get some iteration and understand the regular pumping lemma with some examples, we can do that. I think that might be the best place to go, especially ahead of preparing for Friday's exam.
So it is gonna be on Zoom?
Not this. So through NPDAs, I don't even. Did I say DPDAs on the study guide? I don't think so. So yeah, focus on being able to generate context-free grammars and draw and understand non-deterministic pushdown automata, but that's where the material for the exam is. All right, we'll get significant experience with regular pumping lemma tomorrow. Some more examples, mistakes that I saw in homeworks, etc. I have office hours starting now in case you would like some extra practice with that today.
Probably would come by today, but this one.